In this next video, we are going to talk about improper integrals. And these are a specific case of integral that you're going to be looking at, especially when it comes to some of the word problems that we've talked about, like present value, future value, or total value. An integral defined over an infinite region is called an improper integral. And there are basically two types of these. In the first case, we are looking at a region where there may be a vertical asymptote, and so when I look at the function, whatever the function may look like, if my interval from a to b includes that vertical asymptote, then the region that I'm looking at over that interval is going to be something infinite. And in this case, we can see as it goes off to whatever this value c is, it gets closer and closer to infinity as the lines get closer and closer to c. Okay, so there's one example of an infinite region that we may need to take the integral of. The second case is along the same lines, but now we're looking at something that's not necessarily a vertical asymptote. So let's say my region happens to be infinite because my interval is infinite. And so let's say I was looking at a function that does something like this, where my region is going from a off to infinity. Okay? And so again, because it doesn't actually touch, in this case I'm looking at a horizontal asymptote, because it doesn't actually touch the y-axis, as I get further and further out, I'm always going to have a little bit of a region in there, but it becomes an infinite region. And so those are the two cases that we're looking at. Okay? And in this first case here, basically what we're going to be looking at are things like, again, where I have a defined interval, but maybe my function is undefined somewhere. So something like 3x over x plus 2, where a and b are, say, from -3 to 1. And so here we can see if I looked at this particular interval at x equals -2, I have something undefined, but -2 is within my interval. And so here we're looking at a picture something like that. In this case here, what we're looking at is more along the lines of something like this, where I have an infinite interval, but my function is defined everywhere. So let's say maybe I'm looking at, we'll go from 1 to infinity of 1 over x dx. Okay. So here we can see my function is only undefined at 0. On the interval from 1 to infinity, it's defined everywhere, but now because I have an infinite interval, I'm looking at the second case. Okay? So, two words to keep in mind here. If the value of an improper integral is a real number, then the integral is said to converge to that number. Okay? So if I have an improper integral, a to b f of x dx, and this is some improper integral, either because of the first type or the second type, it does not matter which. But if this comes out to be some L, where L is a real number, then the integral from a to b of f of x dx converges to L. Okay, so that's another way to say what we've written here. If the value of an improper integral is plus or minus infinity, or it does not exist, okay, and we'll talk about why it may not exist in a little bit, but if I get something infinite or something that can't be defined as a real number, then the integral is said to diverge. Okay, and so here, if I get something like a to b of f of x dx is equal to positive infinity, then we say the integral diverges. Okay? And notice the different notation here. When we say it converges, we usually say what it converges to. When we say it diverges, we just say it diverges. And that just means that there is no real value for the area under that curve. Okay. All right. So now let's look at a couple of examples of improper integrals. And as we look at these examples, we'll talk about how to go about solving these and looking for the problem areas of these integrals. Okay, so in this first one, we're looking at the integral from 1 to infinity of x cubed dx. And this is our second type of improper integral, where I'm looking at something over an infinite region. And again, I can see here, even though x equals 0 is problematic in this function, notice there's no places on the particular interval that are undefined. And so here, because it's an infinite region, again, when I think of taking the antiderivative and plugging in, I'm not going to actually be able to evaluate at that upper limit, because it's not a number, it's an idea or a kind of an intent. So here, what we're going to do is we're going to start by rewriting our integral. And to do that, I want to make it so that it is something I can actually use my fundamental theorem of calculus on. So to do that, instead of looking at an infinite interval, I'm going to take the limit as, say, m goes to infinity, and here you can pick any letter you want. It's just going to be a representation of that value up there, of 1 to m 1 over x cubed dx. Okay? And again, the idea behind rewriting it is because now if I ignore the limit for just a moment, this is just a regular interval. I have a finite interval, and I can integrate this over that finite interval. And once I've done that, then I'm looking at a function for which I can take the limit. Okay? So here we're going to go ahead and find our antiderivative. So here I can think of this as x to the negative 3. So my antiderivative is going to be a negative. So taking the antiderivative here, I'm going to go ahead and rewrite that limit. My antiderivative is going to be a negative 1/2 x to the negative 2. So again, you can think of that as x to the negative 3. And I want to evaluate that from 1 to m. Okay? So by our fundamental theorem, plugging in at the upper limit, it looks like negative 1 over 2m squared, minus at the lower limit, I'm going to get a negative 1/2 over 1 squared. Okay. Which we can simplify. Limit as m goes to infinity of a negative 1 over 2m squared plus 1/2. Okay. And now, like I said, we have a function that I can take the limit of as m goes to infinity. And so here we can see as m goes to infinity, the denominator here is going to get really big, which means the fraction is going to go to 0. So here we get the real number 1/2. So this tells us the integral from 1 to infinity of 1 over x cubed dx converges to 1/2. So in this next example, let's look at the integral from 1 to infinity of 1 over the square root of x dx. Okay. And so here again we can see, again the only problem area is x equals 0, but again that's not in my interval. On my interval from 1 to infinity, the function is defined everywhere. So I want to use my limit again. I'll look at the limit as m goes to infinity of the integral from 1 to m of 1 over the square root of x dx. Okay. Now again, this 1 over the square root of x we can think of as x to the negative 1/2. So we can find our antiderivative. So x to the negative 1/2, we'll add 1 to the exponent, which is a positive 1/2, multiply by that new reciprocal of that exponent. That's going to be evaluated from 1 to m. Okay. Again, we'll use our fundamental theorem. Okay. Okay, so plugging in at the upper limit, we get a 2 square roots of m minus, at the lower limit, 2 square roots of 1, which again we can simplify. Okay. Again, we have a function. We can take the limit as m goes to infinity. Okay. And in this case, we can see as m goes to infinity, well, 2 is just going to remain 2, but 2 square roots of m, well, that's an increasing function, so that's going to get big. So this is going to go off to positive infinity as my m goes to infinity. So here, the integral from 1 to m of 1 over the square root of x dx diverges. So before we go to the next example, I just want to mention it doesn't matter that I had an infinite interval as to whether it converges or diverges. So here, if you notice, the intervals are exactly the same in both cases, but one function is going to converge while the other diverges. So it really does mean that you're going to have to actually evaluate these and take their limits to figure out what it does. You can't just tell based on the interval. All right. In this next example, this one is a little different than the previous two. First thing we notice is that the interval that we're looking on is not infinite. So we're actually looking on finite interval. These problems are probably the hardest improper intervals to solve. And that's because if I look at it, it looks like any other integral I've done up till now, right? We've got a finite a and b. And if I look at it, I've got some function, okay? The main difference here is that my function is not defined on the interval, okay? So here, if we note, x squared minus 1 equals 0 when x equals plus or minus 1. So at x equal 1, which is in the interval from 0 to 2, this is not defined. Okay. And again, that's not always obvious unless you take a second and actually look at that. And this is one of the reasons I would suggest for any function, if I'm going to do an integral or a derivative, the first thing I should look at is probably whether or not the function is defined on the interval. Okay? In this case, because it's not defined at 1, again, this doesn't necessarily mean that the function, the integral, it diverges. What this means is I need to break this up, just like we did with the area problems, and look at each half of the interval. Okay? So here, I'm going to start by breaking this up. It's going to be 0 to 1 of x over x squared minus 1 plus the integral from 1 to 2 of x over x squared minus 1. Okay? And again, we do that because 1 is the problem area. And again, if I notice here, I still can't evaluate this at 1, but I can do like we did over here and use the limit to define these. So I'm going to let m go to 1, and I'm going to look at the integral from 0 to m of my x over x squared minus 1. And then I can do the same thing for the second interval. So as m goes to 1, I can go from m to 2 of x over x squared minus 1. Okay. From here, we'll go ahead and take our antiderivative. Here, you're going to need a u substitution to get that antiderivative. So let your u be your x squared minus 1, and then go from there. So we'll get a limit as m goes to 1 of a 1/2 natural log x squared minus 1. That's going to be evaluated from 0 to m. Notice the antiderivative is going to be the same in both integrals. First one will integrate from 0 to m, the second from m to 2. Excuse me. Okay, now we'll use our fundamental theorem. So plugging in at the upper minus the lower. So at our upper limit, we're going to get a 1/2 natural log m squared minus 1. Now m squared minus 1, m is always, m squared is not always bigger than 1, so here you do need your absolute values. Minus, at the lower limit, 1/2 ln, plugging in 0, we'll get the natural log of absolute value of -1, which is just 1. Plus, same thing, and here I can go ahead and drop the second limit, because now everything's going to be evaluated at 1 once we take these limits. So at the upper limit here, we'll get a 1/2 natural log 2 squared minus 1, which is 3. There I can drop the absolute values, because that is going to be positive. Minus at the lower limit, 1/2 natural log m squared minus 1. Okay, that whole thing we're going to take the limit as m goes to 1. Now again, here I probably want to clean up before I take my limit. So one of the things you should notice is I've got basically the same term, just a different sign. So those natural logs of m squareds minus 1s are going to go away. This term here, 1/2 ln of 1, that's just 0. And so I'm looking at the limit as m goes to 1 of 1/2 natural log of 3. But in this case, there's no m in there, so this is just 1/2 the natural log of 3. So our integral from 0 to 2 of x over x squared minus 1 dx converges to 1/2 the natural log of 3. Let's look at one last example of improper integrals. So this example is going to be a application type problem, similar to the ones we saw in section 7.4. So in this case, revenue from the sale of new homes in the U.S. decreased dramatically from 2005 to 2010. The model, R of t equaling 412 e to the negative 0.323t billion dollars per year for 0 less than or equal to t less than or equal to 5, gives the revenue for year t since 2005. If this were to continue into the future, we want to estimate the total revenue from new home sales from 2005 and on. Okay? So if we look at this, we can see that we're looking at a future value type problem. I take that back. We are looking at a total revenue problem or a total value problem, but we're looking at a start of 2005 and then we're continuing on. Okay? So here, our total value is going to be set up. It's the integral from 0, and since there's no end date, we're going to go to infinity on this. Our function, R of t, is the 412 e to the negative 0.323t dt. And again, remember, for total value, that's it. I don't have to add on an extra e to the exponent or anything like that. It's just our revenue stream. Okay. So in this case, again, the first thing we notice is it's an infinite interval. So we have to start by rewriting this as a limit. And now we want our antiderivative. And again, here we notice that the function itself is continuous on the interval. So finding the antiderivative should not be a problem. And so in this case, again, we'll need a u substitution. We'll get the 412 over to the negative 0.323 e to the negative 0.323t. And we're going to integrate that or evaluate that from 0 to m. So to clean this up, negative division of that decimal is probably not going to be very nice. So here we're going to go ahead and plug in and then evaluate everything all together. That way we don't get any rounding error. So at our upper limit, we'll get the negative 412 over 0.323 e to the negative 0.323 m minus at the lower limit, that negative will make that a positive 412 over 0.323. E, plugging in 0 for a limit, just gives us e to the 0. Okay. Notice here e to the 0 is just 1. So we're looking at the limit as m goes to infinity of 412 over 0.323 minus 412 over 0.323 e to the negative 0.323 m. Now as m goes to infinity, we'll see that this term, as m gets big, this is going to become more and more negative. E to a really big negative number becomes really small. So this term is going to go to 0. Okay. And so here we're looking at 412 over 0.323 when we take our limit. So our total value is going to be $1,275.54. We have to be a little careful here, because if we go back to the original, this is in billions of dollars. So we're looking at $1,275 billion about. Okay. So there would be our solution. Okay. Again, very similar to what we did in the previous sections. The only difference is because now we're looking at an infinite interval, we have to rewrite this as a limit in order to solve.